the last presentation we discussed about some commonly used pickups known as velocity pickups and accelerometers. In this presentation we will discuss very briefly, almost in a sketchy manner, of various types of transducers which can be used in special circumstances. Some of them are contact type, some of them can be non-contact type. So we continue with our discussion on vibration measurement. First, I think let us take a non-contact type pickup based on electromagnetic induction. The basic scheme So this is the coil which is wound about one leg of this magnet. This is the magnet, permanent magnet. This is the vibrating surface. It has to be ferromagnetic. This is the gap maintained. And this is vibrating. Now what happens? Let us see. We know very well that the flux, or whatever we may say, magnetic flux, they complete their path to this. Like that. Now if that be so, and the intensity of this here, it depends on what is the gap. So as the gap fluctuates, what happens? The flux changes. And since this coil is there, and we know from the basic theory of electromagnetic induction that when the flux inside a coil fluctuates or changes with time, a voltage is developed. So that means what we will get? We will get a voltage generated here. And this voltage we know is given by this one. That means the number of turns now this flux, as you know, is function of the gap, and this we may say as x cosine omega t. So therefore, we can write this as minus n. Now d phi dx, that means this quantity, that means which the flux depending on this gap which is given by this quantity is a quantity dependent only on the configuration of the whole thing, dimensions, material and all those things. And this obviously is dx dt, so therefore which is x dot. So therefore the voltage which we get is proportional to the velocity of the object. So it is again a direct velocity pickup. So what we will get, that means the sensitivity, that means the voltage divided by the velocity is called the sensitivity. And we may use some unit like say millivolt per centimeter per second. Centimeter per second is the velocity and voltage is in millivolt. So this, therefore, this contact, the gap, this remains fairly constant. One thing we have to keep in mind, that this is not going to remain a constant quantity unless this vibration amplitude is small compared to the gap. That means the gap is not changing much, and this the gap is maintained in the range 3 to 5 millimeters. And the amplitude of vibration x is a small fraction of gap. In that case, this remains fairly constant and the voltage which we get, E, becomes proportional to x dot. And this ratio is considered to be the sensitivity of the pickup. Now, to get some idea about the typical sensitivity, we plot the sensitivity in millivolt per centimeter per second unit. So this is 0, 4, 8, 1, I think. Hundred, sorry, 10, and then this will be 100. This will be sensitivity in millivolt per. So if we plot this, what we will get, something like this. So fairly straight line, but not exactly a straight line, but this is the kind of characteristics for a pickup. But one thing we can see, that the change in gap changes the sensitivity quite drastically. So what we will get, that here, unless the vibration is extremely small, but normal case, then you will find that this is not exactly a constant, and therefore we cannot say E will be proportional to x dot. That means what? It introduces certain amount of nonlinearity, because this itself is a function of x, not a constant. So E cannot be a linear function of x dot. So it will be nonlinearity will be introduced. There will be certain amount of distortion of the shape of the waveform, what we will get here, and the actual vibration, they will not match exactly. Now again, another point we have to keep in mind using ferromagnetic pickup, that here this material will have to be a ferromagnetic material. There can be an object, there can be an object which is vibrating and we want to measure its vibration, but it is not made of ferromagnetic material. In such case, what we do, try to solve the problem by this technique. So if this is the material which is not a ferromagnetic material, say plastic or brass or something, it's not steel kind of thing, then what we do, we attach a ferromagnetic piece, and so the vibration of the original body is also vibration of the ferromagnetic plate we have attached. So slight modification of the object has to be done to use this principle. That is the way. So when the system is not too small, then it is possible to use this technique. Next type of vibration pickup which you can use is based on a phenomena which we call magnetostriction, and these pickups are called these are of course contact. What is magnetostriction? I hope it's all known to you, but I will give a very quick reference. Now, when you enter some substation or such installations where there are no moving parts, but there are only transformers, which are again only stationary objects, but still we get some humming sound. Or for example, when there is a motor, somehow if the motor gets jammed, so there is no rotation, but when current is flown, alternating current, we get humming sound. Now what is this? Now this is nothing but the result of magnetostriction. Magnetostriction means if we take a ferromagnetic object and it is subjected to some magnetic field, so when a current is passed, what happens? This will be magnetized. So what may happen? This length of this object may undergo a small change. Now this delta by L, coefficient of magnetostriction, L being the length of the object, as a function of the magnetic field, this is a property of material. Like say for example, most ferromagnetic materials indicate certain degree of magnetostriction, and this change, so when we supply an AC alternating current, the magnetic field in the object varies, fluctuates with time, and so therefore the length of the object will also vary, though the amount is extremely small in micron range, but still when it is there, it can produce a sound. And this phenomena, that means where a voltage induced produces a strain, is called magnetostriction. The other effect, the reverse is also true. That means if we take a magnetostrictive object and try to apply some force or stress, and change the length. So the length changes. So this will then generate, if there is a, then it will generate some magnetic field. So inducing a magnetic field in a ferromagnetic material changes its length. Similarly, changing the length by some stress, causing a strain, generates a magnetic field, reverse. So this phenomena is utilized in this type of pickup. The basic principle of the pickup is like this. This end is subjected to vibration. This is the magnetostrictive material, where this is the south pole, this is the north pole, or that means this is so what will happen now? You will find a voltage will be generated. Now, if we consider this magnetostrictive material, this magnet, this is subjected to a load. What load? This side of course is connected to the original body, and the other side is connected to this seismic mass. So this will be subjected to stress due to the inertial loading of this mass. So if it is a cyclic or periodic phenomena, then the flux here will fluctuate, because this stress will produce some extra flux due to magnetostrictive effect, as I have mentioned. Therefore, d phi dt, which is going to generate this voltage, will be proportional, is equal to d, and phi, which is a function of sigma. Now, how much is sigma? Sigma is equal to the force by area. How much is this force? Force is mass into x2 dot divided by area. Now, the voltage generated is proportional to d phi dt, or d phi dt can be written as d phi d sigma dt. So effectively E becomes proportional to, you see, d phi d sigma is a quantity which depends on the configuration, dimensions, material and so on. That means the system or the equipment property. So, it can be treated to be something constant for a particular experiment. But d sigma dt will be what? Will be proportional to x3 dot. So, therefore, the voltage what we get here is proportional to the jerk or the rate of change of acceleration, which of course can be integrated electronically, and output can be either acceleration, velocity or displacement, whatever we want. But basically in magnetospective transducer pickup, the voltage we get is originally dependent on the jerk or the rate of change of acceleration. The kind of this d phi, d sigma, if you want to have some idea, let us plot the characteristic. So, the nature of the curve will be generally something like, so only a small range where we may treat is to be approximately linear. After that it tends to become nonlinear, and as mentioned earlier, we should always try to see or try to get or achieve linear characteristics. If in a particular case, if you want to do, this is the general thing. Sigma in kilogram per millimeter square. Kilogram of force, it is not SI unit which are given in this. And this is the change in induction. In Gauss, this will be 0. Like this, and the realistic values for a particular case. So, you can see that operating range could be very easily this. This again, of course, you can really understand that if you have to attach it to the main vibrating body, this becomes a contact type pickup. Next, we take up another type of pickup, which is again a non-contact type pickup, and which are generally used for special purpose situation or special purposes, and they are based on the variation in capacitance due to the variation in gap, because any vibration, that is mechanical movement or displacement, can be somehow be translated into the variation in the capacitance of the system, and that can definitely produce some electric signal. . 。 . 。 . 。 . basic principle, as you can see, is very simple. If the surface of the object is vibrating, we place another plate parallel to this, very near to this, and this capacitance of this system produced by the two surfaces, nearby surfaces. So they form a capacitance, and that variation in the capacitance is to be measured. Now, one thing is very clear in this case, that such type of devices cannot be passive type. In the all other previous cases where we generated some voltage which did not require outside source, the voltage was generated by the process itself. In this case, that is not going to be the case, and we need to have an arrangement for so the circuitry which has to be used. The basic principle looks like this, that we have to supply a bias voltage through the DC source, which is connected across this gap with the help of a very high resistance 10⁶. And then, since the whole process is a dynamic process, and we cannot just attach it, because then the instrument itself, this impedance will affect the current through this. So what is done? A blocking capacitor is given here. So the variation in capacitance here generates a fluctuating voltage. The device, this particular device also will have nonlinearity, mainly because the capacitance is very sensitively dependent on the gap, and that makes the situation nonlinear, and also the signal produced will have some distortion. One more thing to be kept in mind is that generally capacitance variation is used as special purpose cases. Standard capacitance pickups are rarely used and rarely available. So when a particular situation is somewhat special, and then this principle can be used in picking up the vibration. So the next type of pickup is based on mutual inductance, and which is also again a non-contact pickup. So here we do what there are two coils around same core. One is primary coil and other is secondary coil, and if we can, and we also pass a primary coil current IP, so that a field is established. Now, if by any chance we can change the mutual inductance, we can generate the voltage in the secondary one. And this changing this mutual inductance between the primary and secondary coils, let it be Lm. So let if Lm be the mutual inductance, then the voltage which you will be able to generate will be equal to mutual inductance omega to IP, where IP is a high frequency primary coil current whose frequency is omega. So this is not a DC, actually it is a very high frequency current to the primary coil whose frequency is omega. In that case, if the mutual inductance be Lm, the voltage generated here will be E. Now, what happens? This gap, which is a metal, and due to the eddy current which is generated here, it produces an effect which changes the Lm. So, what will happen is interesting, that so if this is a very high frequency current will produce a voltage E, something like this. Now, this fluctuation is because the mutual inductance is varying due to the variation of this. Therefore, this modulated output which you are getting, if you demodulate it, you will get a fluctuation like this, which represents the vibration of the object which you are trying to measure. So, mutual inductance variation can be made almost linear over a displacement range up to approximately 5% of coil diameter. If the amplitude of vibration is kept within 5% of the coil diameter, then the mutual inductance variation can be made approximately linear or approximately proportional to the displacement or the gap. So, therefore, the shape which will generate will not be much distorted, and we will get a reasonable degree of faithfulness of the result. So, this is also, of course, you can see is a non-contact type pickup, and just to get some idea about the magnitude of the effects, we can take a particular case. The distance or gap in percent of coil diameter. And mutual inductance in microhenry. V 0, 2, 4, or rather I will not use this. Let us put somewhat smaller scale, say it is 1, 2, 3, 4, 5. Otherwise it will be too flat. So this variation then we will see will be almost something like, not exactly linear, but almost a straight line if you leave it or keep it within 5% of recoil diameter. So this is the order of magnitudes involved, which can give better idea about the kind of quantities involved. So there are many other types of pickups. I must say there are varieties, say whole branch of engineering one may say, by sensing vibration, because it is used not only just to measure vibration, it is used for condition monitoring, it is used for sensing the health of a particular machine or a system. So many large number of applications are there. There is another technique which commonly is used in any kind of vibration or dynamic measurement, which I will just briefly mention. That is by using the strain gauges. Now I think again what is a strain gauge etc. are known, but even then I will just give a very quick overview. A strain gauge is a very small, maybe 1 centimeter by fraction of a centimeter long, a paper strip kind of thing, in which is embedded a very thin wire. Now to have a large length of the wire, of course you have to loop it like this. So the total length of the wire is very large and the resistance is measurable, but the overall dimension of this is small. Now what happens if we stick this or glue it to a surface which undergoes extension or something? Suppose if we there is a strain or stress, whatever may be in this direction, then what will happen? The length of total length of the wire will increase by strain, and as a result it will cause a change in the resistance. So your strain and the fractional change in the resistance, they will be proportional. So therefore this quantity, that means change in resistance as a fraction of its resistance by strain, is something called gauge factor. In the ordinary strain gauges it can be of the order of 2 or 3, whereas in semiconductor strain gauges it can be a couple of hundred. Anyhow, now this change in thing, that means it is very suitable for measuring strain. So let us see how we can use it. If we have to measure the vibration, say, of a cantilever beam, as an example. These are the two views, one top view, one front view. This is the top view, this is the front view of the same cantilever beam. Now when it vibrates, vibrating means it bends. When it vibrates, the transverse direction. What happens? It stretches like this when it goes down. So the outer surface will be extended and the lower surface will be compressed. Similarly, in its upward half cycle, this will be subjected to tension and this will be subjected to compression. Now, if we now apply strain gauges, say like we put one strain gauge here, one here on the top surface, and so therefore in top surface we have 1, 2. In this view they will look like this. Similarly, in the bottom surface we will have 3 and 4. So during its bending, 1 and 2 are undergoing tension, that means resistance will increase. Similarly, in this side when it is under compression, resistance will decrease. Now this is used in the form of a bridge and a voltage is generated in this manner. Now resistances or the strain gauges I am representing like this. Not that they are physically kept like this, but just electrical circuit point of view I am just placing like this. So if it is 1, it will be 2, 3, 4, and the circuit which we will have this kind of arrangement, that means which is called Wheatstone bridge. On principle, we could sense the resistance variation of only even one strain gauge, but the sensitivity will be low. The sensitivity can be improved or the electric signal generated can be made much more if we use the concept of a Wheatstone bridge, where this is strain gauge 1, this is strain gauge 2. So when it is going downward direction, here the change in resistance will be delta R, here also it will be delta R, here it will undergo compression, so this will be minus delta R, this will be also minus delta R. So in the condition when it is balanced, that means all of them are undeformed and resistances are R, then if we apply a voltage here, the output voltage will be 0. But now if it starts vibrating, what will happen? The unbalance will be created. At any instant, you can see the ratio of this and this, and ratio of this and this will have maximum difference, because this resistance is increasing, this is decreasing, and this is decreasing, and this is increasing. So therefore what happens is that effectively the voltage which is generated is 4 times, and which is given by this quantity. and then this output can be taken to any recorder or oscilloscope and can be studied, and that means the vibration, the frequency, amplitude, everything can be studied. Of course, we have to keep in mind that in all such instrumentation and measurements, it is essential to have proper calibration. That means we have to give some known deformation and then find out the voltage, so that when we measure the voltage, we know that how much deformation or strain has been created. So this type of strain gauge use is very wide, and in many cases, when a machine or something is vibrating where we cannot put any pickup or something, we can always scrape the surface and we can attach a proper strain gauge, and we can sense the strain which is subjected to, or the surface is subjected to, and that gives us the idea about the vibration it is undergoing. So this brings us to the end of our last module, where we have studied measurement, but as I mentioned, it's a huge subject. The instrumentation we have not discussed, circuits we have not discussed, and only some basic principles of some commonly used transducers we have discussed in this presentation.